Hello everyone. Today we'll talk about the solution to the problem find eventual safe states. When you read the statement, if you're at all familiar with DAGs, which are directed acyclic graphs, and in particular, if you're familiar with topological sorting, which is one of the most common procedures employed on directed acyclic graphs, you essentially get the solution for free because it's one of the most common operations, and indeed the solution here is just a topological sort. In particular, it's the topological sort where you try to sort a directed graph, and at the end, if you don't get all the nodes, that means that the remaining nodes are part of a cycle, and indeed you don't want to return them. Because you see here the topological sorting happening, since we either get nodes that have no outgoing edges, or nodes for which all the outgoing edges are going into the nodes we've already marked, and so on, until we cannot mark any more nodes. So this is exactly just the topological sort. We cut off everything that has no outgoing edges for as long as we can. And we just want to return the list in ascending order, so essentially this is a topological sort, but we don't care about the order, but we care about things not lying on a cycle. So the implementation can go something like this. We want to have the length of our graph. We also want to have the graph with the edges directed in the opposite ways to update the degree. So we'll be creating this reverse graph and we'll be maintaining the degree for every node. So we want this degree to be 0. This is the out degree of a node. And we'll be reducing it by removing edges when removing nodes. And now for every node, the degree we just take from the graph. And now we add, for every neighbor in the original graph, we add our node as a neighbor in the reverse graph for that neighbor. So it's clear what revg is. We turn every edge around. And now we'll be maintaining in the variable q all the nodes that can be topologically sorted. So at the end we'll just return the sorted version of q. At first we take everything that has the out degree of 0 at the beginning. So notice, for instance, that if nothing has out degree 0, then there is nothing in the result and we can just return the empty array. So we take all the nodes for which the out degree is 0, and now this is the core logic of a topological sort. We can go through all those nodes and remove them from the graph, and by removing them from the graph, we look over all the neighbors in this reversed graph, and we can subtract 1 from their degree, because the node current doesn't exist, so the edge also doesn't exist. And that might make this neighbor a node that has no outgoing edges. So in that case we add it back to the graph. So this is the whole topological sort. We don't have to do anything special about nodes lying on a cycle, nodes that are bad, because this topological sort will just skip them. They will never get added to the queue. They will run out of elements in the queue, and that's it. Also, side note, since this is Python, iteration works in Python. The list itself has an internal iterator and will be returning next and next elements, and will be modifying the end of the list. Then there is no problem in the fact that we are modifying the list here while iterating over it. That's completely legal in Python for lists and for many other data structures because of the semantics of iteration.